In Lecture 10, we're going to be looking at some of the basic identities for trig functions, which means there's a relationship between different trig functions that's true no matter what angle you plug in. We're going to use these identities to help us find some of the trigonometric functions if we know other trig functions. Because of their relationship, we're able to figure out one trig function value from knowing other trig function values. If we're given one trig function value and maybe what quadrant it is in, or a sign of another trig function, meaning its positive or negative value, we can actually use that to find all the trig function values. So we're going to do that. And also even and odd properties. We're going to come back and talk about the fact that we discussed even and odd properties for functions in earlier lectures. We're now going to apply those terms to our trig functions. Some are even, some are odd. The first set of identities that we're going to look at are actually ones we're already familiar with because they come straight out of the definition of the trig function values. The reciprocal identities tell us what the relationship is between sine and cosecant, secant and cosine, and cotangent and tangent. You'll remember that in our definitions we learned that cosecant of theta, of an angle, is 1 over y. But we also know that y is sine of theta. So no matter what theta is, cosecant is always going to be the reciprocal of sine of theta. That's why the reason we call it reciprocal identities, because 1 over a number is the reciprocal of that number. So cosecant, sine are reciprocal functions of each other. Cosecant is 1 over sine, secant is 1 over cosine, and cotangent is 1 over tangent. Now the reason we know that is because tangent is y over x and cotangent is x over y. So they are reciprocals of each other, which is why we can say this right here. Now, the other relationship comes straight from these last two formulas that I just wrote down, remembering that y is sine and x is cosine. You can actually see that tangent of an angle, no matter what the angle is always going to be sine of that angle over cosine of that angle. Tangent is sine over cosine. You'll want to remember that because we're going to use that a lot throughout this course, and in any application of trigonometry that's going to come in handy to know. Additionally, cotangent is the reciprocal of that, so if tangent is sine over cosine, then cotangent is cosine over sine. Now notice how we can use some trig function values to find the other trig function values. In this case, we don't even know what theta is, and by the way, this should read cosine of theta is equal to 2 square roots of 5 over 5. Nevertheless, without knowing what theta is, we can still find what, say, tangent of theta is. Right? Because tangent of theta is sine of theta over cosine of theta. And we know that sine of theta is square root of 5 over 5. And cosine of theta is 2 square roots of 5 over 5. Which is enough for us to evaluate now. Square root of 5 over 5 times 5 over 2 square roots of 5. Because dividing by a fraction, you multiply by its reciprocal. If we cancel out some common factors here, 5 divides out with 5. Square root of 5 divides out with square root of 5. If all the factors on top cancel out, you're left with a 1. On bottom we have just 2. So tangent of theta, whatever angle it is that gives me square root of 5 over 5 when I take its sine, and 2 square roots of 5 over 5 when I take its cosine, the tangent of that angle is 1/2. And we can also use reciprocals to figure out the rest. So let's do secant of theta. That's the reciprocal of cosine of theta. So that's 5 over 2 square roots of 5. 5 divided by square root of 5, remember, is square root of 5. So you end up with square root of 5 over 2 here. Cosecant of theta is 1 over sine, which means the reciprocal of sine. The reciprocal of square root of 5 over 5 is 5 over the square root of 5. 5 divided by square root of 5 is just square root of 5. And then cotangent of theta is the reciprocal of tangent of theta, which we already know is 1/2, so 2 over 1, which is just 2. And we've found our other 4 trig function values by knowing only 2 of them. There's another identity that comes straight out of the definition. Once you recognize that the definition of the trig function is based on the unit circle, all you got to do is remember that, first of all, the x-coordinate on the unit circle for that particular terminal side of an angle is the cosine of that angle, and the y-coordinate is the sine of that angle. So x comma y is actually cosine of theta and then sine of theta. But the other thing that we know about x and y is it's a point on the unit circle, which means it has to satisfy the equation of the unit circle. The equation of a unit circle is x squared plus y squared equals 1 squared, or x squared plus y squared equals 1. If I just rewrite that in a different order, and then remember that, again, sine of theta is y and cosine of theta is x, then this says that sine of theta, just plugging in for y, squared plus cosine of theta, that's cosine theta squared, is equal to 1. This is a fundamental identity that we will use over and over and over and over again. By the way, going forward, just for ease of notation, anytime I want to write sine of theta squared, I'm going to write that in this way. Sine squared of theta means the same thing. So when I square the sine, what I mean is take sine of theta and square it. Which, by the way, what you don't want to write is just this. You see, the problem with that is this looks like sine of theta squared, that is sine of this guy, and then you take the sine of it, right? Sine of theta squared, which is not what we intend to mean. In fact, we want to square the sine of theta. So this is the notation we're going to use. So right here, all I've written down for my first fundamental identity is that the sine squared theta plus cosine squared theta is always, always, always equal to 1. So given any theta, if you have sine squared plus cosine squared, that's going to have to equal 1 because it's a point on the unit circle. Beautiful, right? Fantastic. There's two other fundamental identities which come from this fundamental identity. In fact, look at this guy. If I take sine squared of theta plus cosine squared of theta equals 1, notice what happens if I divide everything by cosine squared. Divide the left-hand side by cosine squared and the right-hand side by cosine squared, which in effect is the same as dividing each term by cosine squared. Look at this guy. What is cosine squared over sine squared? Using your quotient identity from the previous page, that's just tangent squared. Cosine squared divided by cosine squared is 1, and 1 over cosine squared is secant squared, which is this fundamental identity right there. You can also take the original one, sine squared of theta plus cosine squared of theta equals 1, and divide everything by, instead of cosine, divide everything by sine squared. Sine squared over sine squared is 1. Cosine squared over sine squared is cotangent squared. And 1 over sine squared is cosecant squared. Just rearrange the left-hand side, you've got that fundamental identity right there. Okay? So those are some very important identities. This one especially you want to remember, because it will come up over and over again. The other two they would be helpful to remember, but it's actually pretty easy to just remember the first one and then figure out the other two whenever you need them, because you'll need them less often. But if you have them all three memorized, that's going to be fantastic. But if nothing else, you want to know that sine squared plus cosine squared is always equal to 1. In many cases, you're going to be able to use those identities that we've covered, the reciprocal identity, the quotient identity, and the fundamental identities, to help simplify a problem where you don't even have to use your calculator. So look at this example right here where I have tangent of 20 degrees minus sine of 20 degrees over cosine of 20 degrees. In this case, I could go to my calculator and plug those in, but I'd still be producing rounded errors because the angles here are not any of my special families of angles. But what I can recognize is that this right here is in fact tangent of 20 degrees using the reciprocal identity. So what I have here is that the tangent of 20 degrees from here minus sine over cosine is just tangent of 20 degrees, and if you subtract something from itself, you necessarily get 0. So I know that without even going to a calculator for any of those trig values. On the next one, I recognize here that secant squared of an angle is 1 over cosine squared, meaning it's the reciprocal, right? So this tells me that sine squared of pi over 12 plus, I can go and write this out if you need to see it the big way. This is 1 over cosine squared of pi over 12. All I did was replace secant squared with 1 over cosine squared. But 1 divided by that is actually just the reciprocal of the reciprocal, which means sine squared pi over 12 plus cosine squared pi over 12. And this fundamental identity up here tells us no matter what theta is in here, in this case it's pi over 12, sine squared plus cosine squared equals 1. Done. Another thing that we can do, knowing some of the properties of trig function values, goes back to what we were talking about in the last lecture of knowing the trig function value and perhaps the positive or negative value, the sign, S-I-G-N sign of another trig value. You can find all the rest of the trig function values. You don't even need to know the angle itself. Consider this. We have that we know sine of an angle is 1/3, and we know cosine of that angle is negative. The first question I posit is, what quadrant are we in? If sine is positive and cosine is negative, then you know that you have to be in a quadrant that's not the first quadrant, because all things are positive in the first quadrant. So if S for sine is positive, remember all students take calculus, that means we're over here in quadrant 2 in this problem. All right? Now, if we're in quadrant 2, let's see if we can't figure out the coordinates of our point here. Now, if we knew the unit circle value, we know that the y-coordinate is 1/3. But the easiest way to do that is to go back to our theorem that we covered at the end of a previous lecture, was that, say we don't know that it's a unit circle, it's some other circle radius r, we still have the trig function values. Look at this guy right here. That already looks like this thing right here, doesn't it? I mean, it looks like a fraction. So why don't we let y equal 1 and r equal 3? Right? The only other thing we would need to know is x, and we could figure out the rest of the trig function values. But we have this beautiful little equation here that relates the 3 of those values together, x squared plus y squared is equal to r squared. We could figure out x just from this equation, right? X squared plus 1 squared is equal to 3 squared. Another x squared plus 1 equals 9, or x squared has to equal 8, which means x is plus or minus the square root of 8, or simplifying our radical, x is plus or minus 2 square roots of 2. Now, I included the plus or minus here because I've got to know whether or not x is positive or negative in order to find the rest of these. And I can't assume it's always positive because I don't know if I'm in quadrant 1 or not. In fact, that's why we have to know what quadrant we're in. So the first question I answered of what quadrant we're in is the very first step you got to ask. If you can figure out what quadrant you're in, then you can figure out which sign this is. What sign does this number have to be if we're over here? Since x is on the left of the y-axis, we know it's negative. So x is going to be negative 2 square roots of 2. Now, knowing x, y, and r will give us all we need to know to find the other 5 trig function values, right? Cosine of theta is x over r, so that's negative 2 square roots of 2 over r, which is 3. Done. Tangent of theta is y over x, which is 1 over negative 2 square roots of 2. Or if we rationalize by multiplying by the square root of 2 over 2, we get square root of 2 over 4 negative. If we do secant of theta, that's actually just the reciprocal of this, so we can go straight to 1 over cosine of theta, or 3 over negative 2 square roots of 2, or if we rationalize by multiplying by square root of 2 over 2, you get 3 square roots of 2 over negative 2 times 2, which is negative 4. Cosecant of theta is 1 over sine. Sine was 1/3, so we get 3 over 1, which is 3. And then cotangent of theta would be, we could do 1 over tangent, or I think the easiest way to do that is to do x over y. X over y is negative 2 square roots of 2 over 1, or negative 2 square roots of 2. And we now have all 5 trig function values, knowing only one value and the sign of another. Let's do one more like that just for practice. The first question is, what quadrant are we in? We know that tangent is positive and sine is negative, so all students take calculus means we're down here in quadrant 3. So you've got some point down here on the unit circle, not unit circle, some circle, you've got a point down here. Now if tangent of theta is 1/2, we could let this be y and this be x, except that if I did positive 1 and x is equal to positive 2, where am I? I'm up here, right? But I could also do negative and negative to get me down here in the third quadrant. Right, so you got to check what quadrant you're in and then choose the values from the function, right? Remembering that tangent is y over x. Choose the values from the function so that you get this value for that trig function, and you've chosen the right coordinates. In this case, negative 1, negative 2 are the coordinates of that point. But you got to know one other thing. You got to know r to do this. So use x squared plus y squared is equal to r squared, which means negative 2 squared plus negative 1 squared is equal to r squared. So r squared is 5, because that's 4 plus 1. So r is the square root of 5. And by the way, r is always positive. So here's r, here's x, here's y. Now we can write down the rest of our trig function values. So sine of theta, y over r, gives me negative 1 over square root of 5, or negative square root of 5 over 5. Cosine of theta is x over r, which is negative 2 over square root of 5, or negative 2 square roots of 5 over 5. Tangent of theta we already know is 1/2. Sine of theta, sorry, that makes cosecant of theta next, is r over y, so square root of 5 over negative 1, which is negative square root of 5. Secant of theta is r over x, which would be square root of 5 over negative 2, or negative square root of 5 halves. And then cotangent of theta would be 2 over 1, which is 2. Very good. Last of all, let's take a look at our even-odd properties. You'll recall from a previous lecture, the even functions and odd functions are special functions that you can determine their value when you plug in the negative value of an x or a theta. You get either the function value for just the theta, or maybe the negative of the function value. So, well, here's the definition. Well, let's just write it down. A function is called odd if f of negative theta always gives you negative f of theta. You know, our basic example of that back in our earlier functions, our general review of functions, was x cubed. In fact, any odd power is an odd function. So x to the 5th, x to the 7th, x to the 9th, those are all odd functions because f of negative x would be negative x to the 3rd, but a negative times itself 3 times gives you a negative answer. So that actually is the same thing as just taking negative of the f of x. So for example, f of negative 2 is the same thing as taking f of 2 and then putting a negative in front of it. F of negative 3 is the same as taking f of 3 and then putting a negative in front of it. Well, it turns out a majority of our trig functions are actually odd functions. For example, sine is an odd trig function because sine of negative theta is sine of theta with a negative in front of it. You can basically pull the negative sign out front of these 4 trig functions, but only these 4. Now just think about why that has to be true, and we'll consider it with the simplest example of the sine function. Let's say we have this angle right here. That's theta. Okay. If you have some point on the outside of a unit circle and there's your y value, that's your sine, right? That's sine of theta. What does negative theta look like in this picture? Well, negative theta would be the same angle only going clockwise. So what's the y-coordinate of that point right there? Since it's a mirror image, it's going to be negative y, which means you get the negative sine of theta because you're going in the opposite direction. Your y value is negative. On the other hand, your x value is the same for both of those. So this same picture is the reason why sine is odd, but it's also the reason why cosine is even. In other words, an even function is one that if you plug in a negative, you get the same answer as if you had just plugged in the positive. Cosine of negative theta is the same thing as cosine of theta, right? Because if you go the positive direction or the negative direction, your x-coordinate is the same. Whereas if you go the positive direction and the negative direction, your y's turn out to be opposite signs. Okay? So all of these turn out to be true for that same reason. These even trig functions, that is cosine, and then its reciprocal, which is secant, is even. And we can use that to evaluate, simplify the evaluation process of certain angles. Based on the fact that sine is odd, you can actually rewrite sine of negative 45 as just negative sine of 45 degrees. So in this case, I don't even need to remember how to find sine of negative 45. If I can just remember sine of 45, which I know is square root of 2 over 2, then sine of negative 45 degrees is going to be negative sine of square root of 2 over 2. Oh, sorry, negative sine of 45 degrees, which is negative square root of 2 over 2. Cosine being even means negative signs just drop out, right? Cosine of pi, negative pi, is the same thing as cosine of pi. What is cosine of pi? That's this point over here who has an x-coordinate of negative 1. Cotangent of negative 3 pi over 2 is negative cotangent of 3 pi over 2. Cotangent is x over y. 3 pi over 2 is right here, which is 0 comma negative 1. X over y gives me 0. And it's negative 0, which negative 0 is still 0. Last one I got here is tangent of negative 37 pi over 4, which by even odd properties would be, since it's odd, is negative tangent of 37 pi over 4. Now here's where I'm going to take advantage of another property, which is the period of this function. We know that tangent repeats itself every 2 pi, actually repeats itself every pi. So if I took the 37 pi over 4, I could count that out, pi over 4, or, counting that out meaning going pi over 4, 2 pi over 4, 3 pi over 4, 4, 5, 6, 7, 8, until I get to 37. Or I could just take the 37 and divide it by 4, right, I get 9/36 with 1 left over. So I go around 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. I end up at the same thing as pi over 4. And we know tangent of pi over 4 is just 1, so you get -1. And that is the end of lecture 10.